Today we'll be talking about projectile motion. We'll review what we've learned so far, just the one-dimensional kinematics. As we learned last time, position, displacement, and distance are all measured in meters and are vectors, scalars, and vectors respectively with these variables. Speed, oh, speed is a scalar. Um, you calculated delta x over delta t. Velocity velocity is a vector given the variable v with a little arrow. It's given delta x arrow over delta t and also measured in meters per second. And acceleration is a vector given a arrow and is measured this way, or is calculated using delta v arrow over delta t. And it's measured in meters per second squared. Okay. We also learned that if a car is traveling at constant acceleration, position over time is going to be parabolic. Velocity over time is going to be linear and not horizontal. And acceleration over time is going to be a horizontal line.
And then we kind of went over the three basic formulas for kinematics, which is final velocity is initial velocity plus acceleration times time. Position is initial velocity times time plus 1/2 at squared. And vf squared is vi squared plus 2a delta x. And so these are the three big equations that we used last time and we're also going to be using this time. So we're just going to start with one practice problem from last week. I know we went over a couple of them last time, so this is just one kind of review problem just to kind of get in the flow. So maybe you could give about 3 minutes, 3 minutes maybe, to take a look at this problem and then come up with any answers. And if it's too short of a time, just let us know. Maybe you could extend it for a little longer.
Okay, it's been about 3 minutes. Is everyone good?
If you need more time, you can just put it in the chat. Otherwise, I'll just go ahead and get started. Okay. So for the first part, let me just pull up the annotation tool. For the first part, we want to find time, and we're given initial velocity is 3 meters per second. So to do that, we can use this equation over here. You guys see what I'm writing? So you can use that equation over there, because what we know is when the torch comes back to his hand, it'll have the same speed but opposite direction as when it left his hand. So we know actually that the final velocity is the negative of the initial velocity. So we can kind of simplify it to this. And then from there, we have the equation for time is minus 2 times initial velocity over 2 times acceleration. And so plugging in and simplifying, you can just get time is, since the acceleration is minus 9.8 meters per second squared, you can cancel minus from both sides, and you get 2 initial velocity over g, which is 0.61 seconds. So for part B, let me just change the color. For part B, we want to find the greatest height the torch reaches, and when the torch is at its highest point, its velocity is momentarily 0. So again, we can use this equation over here. Vf squared is vi squared plus 2a delta x. And again, we know at the top the velocity is 0, and the initial velocity is given as 3 meters per second. The acceleration is minus 9.8 meters per second always. And so just solving for x, we can rearrange to get, rearrange the equation and get x is vf squared minus vi squared over 2a, and now just plugging in the numbers, that the height is 0.46 meters. So now we know the total time is 0.61 seconds, and it takes the highest point is 0.46 meters above his hand. And so the last part is the height of the torch when the speed is 2 meters per second. And for this part, we can see that our givens are the initial velocity is 3 meters per second, the acceleration due to gravity is minus 9.8 meters per second squared, and now we know that the speed is 2 meters per second. And we want to find the height. And actually, you can see that it follows the same equation as this. We have the same givens and the same unknowns. And so we can do the same kind of rearranging to get that the position is vf squared minus vi squared over 2a. And so by plugging in the numbers this time, we know that the final velocity is 2 meters per second instead of 0 meters per second. And so we can just plug in the numbers and get that the position will be 0.26 meters above his hand. So hopefully you got those answers then.
Any questions before we move on? Okay.
And so the last thing we're doing in review is kind of reviewing the concepts. So we have our mathematical terms, which Mark kind of went over earlier, including velocity, acceleration, and their definitions. We talked a little bit about the models for physics. So these were the graphs. And we didn't get too much practice with the graph, but I think we've posted some problems in AP Classroom. Sorry about that, someone just walked in. So we talked a little bit about graphs in position versus time, velocity versus time, and acceleration versus time. And finally, we just went over the kinematic formulas. And so these are the 3 things that we should kind of be familiar with by this point.
So now we're going to get into some more interesting stuff with projectile motion, again, building off of all the concepts we've been practicing so far. And this is a bit more of a challenging concept. So if you have any questions, feel free to speak up and unmute yourself, or you can put in the chat and we'll try to get to it. So the first part is trying to imagine what is projectile motion. A very common example is when you throw toss a ball up to your friend. And during this motion, it's very similar to what we've been talking about before. It creates that arch where at the peak, the velocity is 0. And this is, again, due to the effect of gravity and the acceleration due to gravity, which is negative 9.8 meters per second squared. And we tend to divide this motion into two main groups, the vertical component and the horizontal component. The vertical component is the part of the motion that deals with it going up and down, and the horizontal is when it's moving right or left, which is the most common axis. And for these two components, there are certain characteristics that are constant throughout. And for the vertical component, we explored this before. It's when it has an acceleration at negative 9.8 meters per second, and the velocity is 0 at its maximum peak. And this is because, as we mentioned before, it has a positive acceleration and it reduces until it reaches 0 and continues to become negative, which is when it goes in the negative direction. And these are the graphs that are associated with the vertical component in projectile motion. As you can tell, this is basically the image that you get when you throw a ball up, like throw a ball to your friend, right? It creates that parabolic image, a curve. The velocity is a constant negative 9.8, or sorry, the acceleration is like negative 9.8 meters per second squared, which causes that straight line with a slope of negative 9.8, as you can tell here. And the acceleration is at g, creating this straight horizontal line at negative 9.8. And again, as we mentioned before, free fall, which is what we focused on last class, is basically the vertical component of projectile motion. It's when you have no horizontal movement.
I'd just like to point something out on the last page. Bring the graphs back up. The point where the velocity graph intersects the t-axis is the same point which the ball reaches the peak of its arc.
Yeah, good point. Thank you for bringing that up. So that's again what Keisha mentioned in the equations, and we apply very often. When the velocity is 0, as you can tell here, which they've labeled as time m, I believe, in this graph, that's when the height is at its maximum. And if you've learned calculus, obviously this is not a calculus-based course, but if you're able to apply those skills, you can tell that the derivative here would be 0. And now the horizontal component. And the horizontal component is much, much, much easier than the vertical component. The main idea to get here is that the final velocity is the same as the initial velocity. And that basically means there's no acceleration unless it's applied, which we'll get onto later on. Another very important idea to remember is that the vertical component is completely independent of the horizontal component. When we're working through these problems, we have to make sure that we divide both up and understand which variables are dealing with which ones, that the acceleration of negative 9.8 is vertical and that there is absolutely no acceleration in the horizontal direction. And these are the graphs that go along with that. As you can tell, it is much easier than the ones before. We just have a linear line for the position graph, and that is because it has a constant velocity. And the velocity graph is also a straight line, as you can tell here. And that's because it does not change. The one at the end is the same as it started off with. And the acceleration is 0. So it's just on the x-axis.
All right, so when we're talking about horizontal and vertical components, basically we're trying to discuss what is parallel to which direction, pretty much. So, for example, the horizontal component is the part of the motion that's parallel to the x-axis. So over here in this diagram, you can see like a cannonball being launched from a cannon, and the initial velocity is parallel to the x-axis, right? You can see that it's parallel to the ground pretty much, and the ground in this case is horizontal. So you can see that it's being launched at 20 meters per second, and that throughout the launch, the v sub x, or the x component of the velocity, does not change, right? The only thing that is changing is the v sub y, because at every moment it's accelerating downward at negative 9.8 meters per second squared, which means that at every second it's gaining another 9.8 meters per second downward for its vertical velocity. So at the very end of the trajectory, you can see that v sub x is still 20 meters per second, but v sub y has now become negative 39.2, depending on how long it took to reach the ground. And then from there, we can use our concept of vector addition, which we learned a while ago, to calculate the final velocity, or the final vector velocity. So you can see that when you add the x component of the velocity to the y component of the velocity, you get the final velocity, or the final total velocity. So that's pretty much how you divide components. Yeah, so here you can just see when we're talking, if you don't know the trig yet, don't worry too much about it. But pretty much theta refers to the angle at which the ball or whatever is being launched relative to the horizontal. In this case, the theta is 0 degrees, right? Because it's being launched parallel to the horizontal. So there is no angle. And if you guys know your trig, you know that cosine of 0 is just 1 and sine of 0 is 0. So pretty much here your v cosine theta is constant, right? Because v times 1 is just 1, or v. So that's why one of them is constant, the other one is changing. Okay, so now in general for a projectile motion problem, you should try and follow these steps until you get comfortable with it. So first, just draw a diagram and just note down everything that you're given, regardless of what it is. Just write it down in some mathematical way, right? So write your knowns, your unknowns, and possible equations you can use. For example, if you're given the initial velocity, you can say v sub 0 equals whatever, maybe it's 10 meters per second. And if you're trying to find the time, you can say t equals question mark. So that'll just help you organize your thoughts. And you can also write down possible equations. So you guys have learned 3 kinematic equations so far. Usually you'll be using one, maybe 2 of them to solve a particular problem. So depending on what you're given, you can choose the appropriate equation. So after you do that, just calculate the components of the velocity, pretty much find the x component, find the y component. This is one of the most important steps, I would say, just because you need to know the components because they are independent of each other. If you can't just work with a velocity that just exists, you need to make it into components so that you can calculate things in the x direction, things in the y direction, and then put them together at the very end. Yeah, so finally, you just solve for the missing variables using the formulas. This is one of the easier steps because you've already organized everything, right? You know what you have to plug in and you know what you need to find. So now you just solve for it, you plug in your values, and you're done with the problem. Yeah, and just one more time, the x and y components are completely independent. So if you're working with the x direction, you do not need to worry about anything in the y direction. But that also means that you need to solve for each thing separately. You cannot simply just you can't just work with x directions and then just put them and then apply the same concept to y directions. Everything must be done separately, and then you need to put them together however you need to at the very end.
So are we doing the problems for them or giving them time to do it on their own?
Probably just read it out and then we can give them maybe 5
Okay.
minutes. Yeah.
A stunt motorcyclist attempts to jump over a river which is 1.5 meters wide, 5.1 meters wide. The bank from which he will take off is 2 meters higher than the bank on which he will land, as shown below. Calculate the minimum horizontal speed he must achieve before takeoff to avoid landing in the river. We'll give you, maybe 3 minutes to solve?
Yeah, and just, again, let us know if you need any more time or if you need some assistance and guidance or hints.
Do you think that was enough time? Everyone good? Okay, well, we'll go over the problem. So the first thing we see is we've got D equals 5.1 meters. So this is important because we need to know, this is probably the most important thing that we need to know, because we need to know how far he can go before he hits the ground. So, and then H is 2.0 meters. We want to find time, or well, we don't know time, but we'll see that that's going to help us out, knowing time. And then velocity, or V naught, which we also don't know. So, as I hinted at, we're going to need to be able to travel 5.1 meters in the time it takes us to fall 2 meters. So we're going to want us to find the time it takes for him to fall 2 meters. So we're going to use H equals 2 plus 0 t. And now it's 0 because they have no no vertical velocity to begin with. Plus 1/2 g t squared. Okay, I'm going to get my calculator because that'll be useful. So, we might, okay, so we have 2 equals 2 plus 1/2 g. Wait, wait, no, this isn't gonna be 2. This is 0, right? Sorry, my brain isn't working. So this is the initial height, and this is the final height. So I'm gonna replace this with D because that'll make more sense. No, I'm sorry. We're gonna make that H1 because why not? So we know that -2 equals 1/2 squared, 1/2 g t squared. So we cancel these out, and we're gonna have 1 over. We'll just call g equal to 10, because that makes things easier. So it's about 1 over, so this is the time it takes, the square root of 1/10, which is about 0.31 seconds, or 32. So we'll just put that here, 0.32 seconds. And I'm going to get an eraser just to erase this so I have more space. Is it making sense so far? Oh yeah, my bad. I can't think today, my bad. It's been brought to my attention. I can't think. Sorry. It's been brought to my attention that my brain really isn't working. Um, so, um, this is embarrassing, sorry. We all make mistakes though. We have 4 equals gt squared, so 4 over 10 is, or the square root of 4 over 10 is going to be our velocity, or our time. So that is going to be around 0.63 seconds. So now we want to find, well, 5.1 meters equals v naught t, right? Or because we need to find the amount of the velocity that he needs to be able to clear 5.1 meters in 0.63 seconds. So we have my annotation is acting up. So I'm going to make a little arrow and say 5.1 equals 0.63 v naught. So I'm going to divide 5.1 by 0.63, and it is about 8.06 meters per second. And that is our final answer. That is his horizontal speed. And let me just make sure the decimal place looks like it's actually there. So that is our final answer. Does that look right? Okay.
Any questions?
We'll move on to the next one.
Okay. If there are no questions, this is problem 2.
So in this problem, an object is launched at a velocity of 20 meters per second in a direction making an angle of 25 degrees upward with the horizontal. So basically just 20 meters per second and the angle is 25 degrees. They're asking for the maximum height, total flight time, and horizontal range. And yeah. I think we can reconvene at like 12:46 for this one. So does anyone need more time? Because I know this was a bit of a longer problem. If not, I'll just get started. So as Srinjoy mentioned earlier, it's really important that we kind of list out all our variables. And so today we're going to try to show a bunch of different ways to do that. So Mark showed kind of a list method where he had all his variables written at the top. This is a different way which works better for some people. It's called like a table method. So you have an x component and a y component, and we have different variables. So you can kind of choose them as you want. I've taken the initial, the velocity at the top, velocity, the final velocity, the total distance in the x direction and y direction, and the total time. And right off the bat, we can write a few things down. So we know that the initial x velocity will be the velocity times cosine of theta. And you can simplify this with the actual numbers if you want. I think that's probably going to be more useful. But for this problem, since it's the first time, I'll just go ahead and kind of put in. Actually, I think, yeah, it'll be more useful if I just put in the numbers. So v times cosine of theta, in this case, would turn out to be 20 times cosine of 25, which is 18.12 meters per second. So you can also, it would be helpful to have a row for acceleration, but it's kind of short in space. So in the x direction, there's no acceleration. In the y direction, we have minus 9.8 meters per second squared. And so if there's no acceleration, we know that the x velocity will be 18.12 meters per second at all points. So we can also go ahead and write that down immediately. And then in the y direction, we know the initial velocity will be v sine theta. So in this case, that'll be 20 sine 25, which would be 8.45 meters per second. And we know at the top, the y velocity is always 0 meters per second because it's the brief instant where it changes direction from going up to going down. And so for the last few things, we know that the time in the x and y direction is one of the only things that will ever be equal. And we don't know that yet, but we know that these two entries will be the same. The distances is what we're going to have to calculate in parts A and C respectively. And the final velocity for y we know is actually the opposite of the initial velocity because it starts and ends at the same place. So we can go ahead and also fill this out with minus 8.45 meters per second. So now we can get started with the problem, and we can keep filling in these entries as we go along. So for part A, we can kind of, we know that we have the initial, we want to find the maximum height. And to find the maximum height, we basically want to find the maximum y distance. And so if we want to find the maximum y distance and we don't know the time yet, we can use the third kinematic equation, which is that one over there. So the final velocity squared is the initial velocity squared plus 2ay. And now we can just plug in the numbers and solve. We know that the final velocity, which in this case is actually the velocity at the top, is 0 meters per second. The initial velocity is 8.4 meters per second squared, and the acceleration is minus 9.8 meters per second squared. And so you can just plug in the numbers and you can get 3.64 meters is what I got, and I think that's also what the answer is. And so now we can kind of also fill out the data table in the y direction. We know the height is minus 3 point, oh, sorry, that's positive, sorry, 3.64. So the highest point will be 3.64 meters above the lowest one. And then, let me see if I can erase this. Oh, does anyone need that up? By the way, I can keep it for, if anyone wants that back, I can also send it in the chat if that would be helpful. For part B, what is the total flight time? So this is where we calculate the time. And again, we can use a y equation to do this because the time will be the time for it to go up and hit the ground again. Or in other words, the time the time will start when the initial y velocity is 8.45 meters per second and end when the final velocity is minus 8.45 meters per second. So we can use the equation with height and time. Over here we have y is vyt plus 1/2 at squared. Again, remember we take this independently, so we're only taking y distance, y velocity, y acceleration, and just plugging in the numbers, we know that the distance from the the total time, the distance when it starts and ends will be 0 because it starts from the bottom and by the end it'll come back to the bottom. So you know the total displacement will be 0. We know the initial velocity is here 8.45 meters per second, and we know the acceleration is 9.8 meters per second squared. So plugging in, we can get 1.72 seconds. And again, sorry, 1.72 seconds. And time is the only one that's going to be constant between x and y. So once you find it for either one of them, you can just write the same thing in the other one. So I'll leave this up for a while. And then for part C, we just have to fill in this last data table, which is the horizontal distance. And to do this, we can again use the same equation that we used in part B, but except we're using it for the x direction. And so what this would do, as you can see, we have x. We want to find the total displacement, so that's the initial x velocity times time plus 1/2 at squared. And again, there's no acceleration in the x direction, so we can just go ahead and cross that out. We can just immediately cross out this term as 0. And so we know that the displacement will just be the initial x velocity times time, and that's 18.12 meters per second, times time, which is 1.72 seconds, and so that's 31.2 meters. And so we now know the total x direction, x displacement, total y displacement, and total time.
Does anyone have any questions? Okay, we will move on. So I just realized that we're heading towards the end of our lesson. This is one last method that we wanted to show you, which is using a diagram. So we'll run through this more quickly than the others, and then we'll have questions. Unfortunately, I don't know if we'll get to Syndra's question, so we'll use that as a warm-up for the next class, if that's okay with everyone. So this question. A golfer is practicing on a range with an elevated tee 4.9 meters above the fairway to strike a ball so that it leaves the club with a horizontal velocity of 20 meters per second. How long after the ball leaves the club will it... Okay, I don't know what that... I think it's will it land on the fairway? And then what is the... Sorry?
I think it was land, yeah.
Yeah, land, okay. And then what is the horizontal distance that it will travel before striking the fairway? So have a shot at that. Maybe I think we can only really give you guys 2 minutes for this one, unfortunately, but we will work through it together. So don't worry about that. Okay, so let's get going on this problem. So the first step for this one is to draw the diagram. Like the others have mentioned, there are multiple ways to get on with the problems, and for some people, diagrams are really helpful. So what we like to draw is the direction in which the velocity is traveling, the value of it, as well as, in this case, we have the height of the t, which is 4.9 meters. Now the first question is, how long after the ball leaves the club will it land on the fairway? So basically that's asking how long will it take for the ball to reach the ground. And to do that, we're going to use this kinematic equation. We have all the variables other than time, as we have the acceleration, the initial velocity, which is 20 meters, and we also have the final position that we want it to land at. Oh, sorry, that's not correct. Oh, sorry. So the velocity is 0 because this is the vertical velocity. And when we solve for time, we rearrange it a bit, and we get that time is equal to 1 second. And using the time will also help us figure out the next question. And what is really helpful when we work with these equations is making sure that we label them slightly different. When the equations are given to us, we usually use x for position because that's the most normal variable that we use for things like position. But when we're working with both the y and x direction, for some people it's really helpful to differentiate them by labeling this as y and this as x to make sure that we have two separate variables. And we use the same equation because we have time, which is 1 second, we now know that. We have the initial velocity, we know is 20, and we have the acceleration, which is 0, and that the initial x is 0. And solving through all of that, again, just plugging and chugging, we get that the final x position is 20 meters. And as you can tell by these questions, a lot of times figuring out time can be helpful. A lot of times, even if you don't know where to start, if it gets really overwhelming, usually time can help you figure things out. And it's especially helpful because time is the one variable that is constant between the y and the x direction, as it doesn't really have anything to do with the velocity. It's a completely independent variable and is constant between the two and helps you relate both of them. How much time do we have left? Oh, okay, wait 1 minute. Well, that's basically perfect. We'll share this slideshow. Here's the question that Sundra was going to present, and we will definitely go through this the next class before we get started. And this slideshow also has some more resources. If you guys want to practice with it, we will share it out later for you guys to work through in case you want a bit more practice. And let me stop sharing. And also for you guys, I will share a Google form, on the Discord chat for you guys to fill out just for some more feedback and